Hello, everyone. I hope you can hear me as always. Welcome to this webinar about the full FEM method for the calculation of properties of sections and about an improvement on the input for Bow imperfections. My name is SCIA Engineer. I am product owner at SCIA for the entire metal side of the software. And previously, I have been doing support at SCIA for 3 years as well. Okay, let's go. Before we start on the webinar, a short explanation on how it's going to work today. If you already follow the webinar, you already know the procedure. During the presentation, you guys are muted. This is because the webinar is recorded and posted on our YouTube channel afterwards. So you don't have to worry about your voice being in there. But if you have questions, do not hesitate. There is a questions box where you can ask your questions in. And from time to time, I will peek to see if there's any questions arriving, and I will answer them. I see one right now. Oh, okay. It's just asking for the PowerPoint afterwards. Good. Let's start off this webinar with the biggest part, which is the explanation about the full FEM method, which is a calculation method for the properties of cross-sections. And before we do that, let's quickly dive into the background in SCIA Engineer and see how the characteristics of cross-sections are handled inside SCIA Engineer. So the first principle to talk about is that these section characteristics are determined into two parts. The first part are the characteristics for biaxial bending and axial forces, which are, of course, the area of our section, the center of gravity, the principal axis, and the moments of inertia. These are all things that can be straightforwardly calculated from the geometry of our sections. This part is common for each type of section you have inside the engineer. There's straightforward calculation and, of course, one simple result to this. Then we have a second part of the calculation, which is about torsion and shear. And these ones actually require a little more attention. There's different methods to calculate and obtain these values for sections. And we're talking now about shear center, the torsion constant, warping constant, and then the warping stresses and torsion stresses inside your section. So this first part is common for each type of section you can find in SCIA Engineer, but then depending on whether you have a multi-material cross-section, like a cross-section with concrete and steel in it, or whether you activate the 2D finite element method, or if you have a cross-section that is thin-walled, which has a center line representation inside SCIA Engineer, or not, the procedure to find out the characteristics will be a little bit different. So the first option path we can have is that we have a multi-material cross-section, because for these we will always apply to the finite element calculation for the properties. Or if you have a section where you activated this option inside the engineer, then you will fall into the right side of this graph. And at first, the properties will be calculated through some existing closed form formulas. These are basic formulas for standard shapes where we know, okay, for an I shape, this is the warping generally, etc., etc. And then, if there are values in the profile library, if you take a section from the profile library and the values are known section properties, then these will be taken and will override closed form formulas. And after that, we will do a 2D finite element calculation. And the results from this, so all the characteristics that come out of the 2D FEM calculation will again take priority above these two other options. So if I'm looking at a section characteristic and I have a closed form formula, I can find it in the library, but it's not calculated through the 2D FEM method, then the value from the profile library is the one that's being used in this case. Okay. It's a bit complicated, but actually the graph in the end will let you know what's happening. If you have a thin walled section, meaning you have a center line representation of the cross section, well, in this case, you can calculate the section characteristics through a 1D approach where you're just using the center lines and you allocate a certain thickness to these lines. And of course, the calculation with just 1D lines is a lot easier. So at first, the sections will be calculated with this 1D approach. If there are closed form formulas available, they will override this 1D approach because they will most generally be better. And if there is a profile library value, this one will again take priority over the preceding calculations. But with the important 10% rule. What is 10% rule? Well, it's there to avoid mistakes when writing over all of the library values, for example, into SCIA Engineer. If you miss a digit in writing over all the characteristics, well, then it will be catched by this rule. So if the profile library value is different by more than 10% from the calculated value, then we will use the calculated value because we will then assume that it's most likely that the profile library value is wrong. And then for thick walled sections, these are sections where we don't have this center line representation and we have not activated the 2D finite element method. It follows the same logic as the thin walled section, only there is no way to calculate the torsion and the shear center properties properly. So there is a simplified formula for the torsional constant, but the shear center, the warping stresses, etc., cannot be calculated, so you cannot check these kind of sections for warping, actually. So in this case, it's advisable to use the 2D finite element method and to activate it. Okay, on to the 2D finite element method then. Currently inside SCIA Engineer, there was already one form of 2D finite element calculation for the torsion and the shear properties. It was called Grasov-Juravsky in the SCIA Engineer software, and it still is, it's still in there. But it actually uses two different methods. For the torsion, it will use the theory from Prandtl, which is using the Sobel analogy, where actually you will take your section and replace the section by, let's say, some film of soap that's held at the edges of your held down at the edges of your section, and then you would put some pressure on the bottom, and you will see which shape the Sobel is going to form. And then if we look at the second derivative of this shape, we see that this function actually is very similar to what the the torsion distribution would be along your section. So this is where he would take out the primary torsion stress distribution. However, this analysis is not able to handle warping stresses. So again, we're not able to have warping stresses with this method. For the shear analysis, we would use Grasov-Juravsky, which is some simplified way of determining the shear stresses in a profile. But the issue with this is that this method is only valid for symmetrical shapes and without big holes inside the shape. Plus, it always remains really a simplification of the way the stresses will be distributed in your cross section. So because the existing method inside SCIA Engineer has some drawbacks, we don't have warping stresses in torsion, and our method for shear is only valid for symmetrical shapes without holes. We have implemented into SCIA version 21 this new 2D finite element method for the calculation of second properties, which is the full FEM method. It's called full FEM because it's going to do an actual finite element analysis. As we know, it's SCIA does as well for your structures, but this time it's going to figure out how the stress is distributed when a certain force is applied to the section. And this stress distribution is determined through the principle of virtual work. This is where we get the equation from, and then we solve this until we find an equilibrium, and that's how we get the correct stresses. The things you need to be mindful of course, is that you need a correct mesh definition to get correct results. A drawback of a finite element calculation is that it's susceptible to getting local stress peaks. So if you have corners in your section, very sharp corners, there's a tendency that in these corners you will locally get some very high stresses, just as you would have when you are working with plates and there is the corner inside your plate, you can also get these stress concentrations there. But the most positive thing about this full FEM method is that it is an excellent method for thick-walled sections of any shape and any material combination. So really big holes, 2 different parts of the sections, 5 different materials, you name it, this method can properly handle it and determine the stresses and the warping stresses, torsion stresses, and shear stresses inside your section. Okay. I see a question. Where do we define the finite element mesh for the cross section? I will show it to you later when we go into the software, if I don't forget. If I forget, just ask again. So, comparison between Prandtl-Grasov-Juravsky, the old method, and the full FEM. As you can see here, for this I section, the difference is really, really small. The highest stress value is approximately the same. The difference is like 2 points behind our comma. But what you do see is that the Prandtl-Grasov-Juravsky method does not see the fact that these flanges will have concomitant values in them, will also have a function in the torsion distribution, whereas on the full FEM side, we see that on top of the parabolic distribution of stresses in our, forgot the name of this part of the cross-section, the web, thank you. We also have a linear distribution of stresses in the flanges. So a bit more accurate representation, but for your check, honestly, it will not make that big of a deal. Where does full FEM come into play? Well, of course, as I told to you, Grasov-Juravsky was very good for symmetrical sections and no large openings. So if we go and look at an asymmetrical section, we see where the simplified method goes into the wrong direction. We see here full FEM having a very, very different value for the peak stress compared to the Grasov-Juravsky method. You also instinctively see that the full FEM has a logical stress distribution of this parabolic rising and falling of the stress in each of the flanges of our L section, whereas this Grasov-Juravsky distribution, it's just making this parabolic shape and then dividing it through the width of a buildable material. So in this corner, it's decreasing a little bit again, and it's seeing this as if, this section is somehow working together like that. But it's not valid because it's not a symmetrical section. So we get a wrong output value. Big difference as well, as I told you, the Prandtl method is not able to, it's only able to have torsion values, but not able to determine the warping values and the secondary torsional moment values. So these are zero, whereas with full FEM, they can be calculated and checked afterwards in the check. Also not a minor difference. And here again, some example of an I section with a little bit of a bigger height in the flange. This is to show you the issue of the local stress peaks when working with the full FEM method. We have here a very sharp corner, so we see that the peak value of the stress is a lot higher than what we would obtain with the Grasov-Jurowski methods. However, if we ignore this little peak and we look at the highest orange value, we can see it's between 90 and 100, which corresponds to the highest value of our Grasov-Jurowski distribution. Yeah. So we have this issue of this local stress peak. How could you solve it? Well, you could implement a little rounding in these corners, and that will remove this effect, this problem of corners and local stress peaks from your full FEM method. What you also see again is that the full FEM stress distribution is way more logical than the Grasov-Jurowski, where again we have this parabolic rising and falling of the stresses, but then they get divided by the available width. So at the level of the web, we get suddenly a real big drop in values and then a big rise again. So that's not a real stress distribution that will be there. However, the value coming out of it is a correct value. It's approximately the same as coming from full FEM method. So it's a valid one to use. And will not give you any troubles further on, whereas this peak value of the full FEM might give you some issues. Okay, final comparison is for thin-walled sections and the full FEM method. If we have a thin-walled section in SCIA, like I said, that means we know a centerline representation that has thicknesses assigned to it. The drawback of this thin-walled option is that you only get a value of the stress at the level of the center line. Meaning that the top and the bottom of your flange and the top and the bottom of your web will always have the same stress value. So like in the corner here where the bottom and the top differ a little bit in value, that's impossible with the thin-walled approach. Which is why this thin-walled approach is only valid for thin-walled elements with a small plate thickness. But they don't have local peaks, and the calculation, of course, with lines is much, much quicker than with the 2D finite element mesh. And if you have a thin plate, the results will be absolutely comparable, as you can see here, 1013, same as on the right side, 1013. Yeah. So when does full FEM become important? Well, if you are not able to have this centerline representation, or if your thickness is too high to be considered as a thin-walled section, and you need to take into account the fact that stresses can vary over the thickness of your plate. So to conclude, when should I use which one of them? If you have a thin-walled section with a centerline representation and the plates are thin enough, go for the thin walls. You will not have local stress peaks. You will have correct values and they will be quicker. But if you don't have the centerline representation or you have a massive section, you can best always opt for the full FEM method. What's the exception? If you're having issues with local peak values because you have corners and you have no way to remove them by adding roundings or whatsoever, It's also still a good option to use the Krasov-Uralski method, but only if you have a section that is symmetrical and not a multi-material section. Okay, so this brings us to mesh size. What mesh size should I use is an often asked question, but generally the defaults made by SCIA Engineer are quite good. I think I'm going a bit too slow. Yes, I am, so I will not go into detail, but use defaults. But if you have problems with local peaks in full FEM, you can try and have a coarser mesh as long as your main value remains approximately correct. Having a coarser mesh will decrease this local peak and give you values that you can work with better. Okay, so let's go to the software, and I will show you where you can adapt the mesh size. So I have a profile here. On the side, you will find the option for 2D FEM analysis. You can print it on. In the old projects, by default, Krasov-Uralski is opened. In the new projects, by default, it will be the full FEM method. And then just below, you can give a specific size to your mesh. If you leave 0, then the default value will be used. Simple as that. And then I talked about the center lines being available and having a thin walled section. It is always something you can see right here. So in this case, I have a thin walled shape. I have center lines available. For the geometrical shapes here, for example, that's not always the case. In this case, I have a thick walled section and I don't see the center lines. That means that if I do not activate the 2D FEM analysis, well, certain properties cannot be calculated or are calculated wrongly. If you see here, the torsional constant is 2.6 e to the 6th. If I activate FEM analysis and I put on the full FEM method and calculate it, first thing we see is that these values are calculated. The second thing we see is that the value for the torsional constant with the simplified method was also completely wrong. So please just remember for thick walled sections to always activate the 2D FEM analysis. And then you can show your mesh if you want to and have a look at how the forces are distributed in your cross section. And here again, you see I've used the full FEM method, so I have a little bit of issue with these local stress peaks. Well, that's all I had to say about cross sections. Let me check if there is any question, or if you have any question, feel free to ask again. I'm gonna pop the question box out. No, I don't see anything entering, so then I will continue with the bow imperfections. So it's a small change that has been made for the inputting the bow imperfections. What has changed is that we have added into the material setup of every material, we have added some default values for the bow imperfections. So if your buckling data of your elements are set to the default option, I will open them for this one. There we go. Then by default, the bow imperfections in there will refer to the value that's been entered in the setup. And then you can open the material setup and you can change this default for every beam inside your project, which, to be honest, is a lot easier than what we had to do previously, meaning we had to put buckling groups on every single member of the structure, and verify that we don't combine the wrong members in the same buckling group, because that could lead to wrong buckling properties for some members. And then change all of these to the Bow imperfections we want. Now here you can just choose a default, and then if there's any members that you would like to change afterwards, you can still go inside the system length and buckling settings and of course override this. So I will now put these Bow imperfections on the elastic option from the Eurocode tables. But let's say I want to ignore this column, or let's say I want to ignore it for some wind bracings because they don't need Bow imperfections, then I can still input some buckling data there and state that for this one, I will not refer to the setup, but I will just not implement Bow imperfections here. For old projects, if you open them, the default will be no Bow imperfection. For a new project, the approach by default will be to have Bow imperfections. Why? Because they're not used automatically. First, you need to choose to use local Bow imperfections in your nonlinear combinations. And we assume that if you want to apply Bow imperfections according to the buckling data, you're most likely going to want to apply them on almost all members of your project. If not, it is quickly changed in your material setups. And this is the same workings for timber, composites, aluminium, and steel. Okay, let me check if there have been some more questions. Meanwhile, I leave you the opportunity to give me some feedback on the development for the metal side, what you would like to see first and where your importance lay. I've also put the link in the chat, and I will look at your questions. Okay, so the question is if there is a way to define when it would be better to apply 2D FEM than to use the 1D method if you have 10-volt section. That's actually you can just calculate this cross section one time with the 1D approach, and then calculate it with the finite element approach, and compare this highest value. If they differ a lot, you have to watch if this highest value is caused by a local peak, because then the issue is probably, is actually on the 2D FEM side and not on the 1D side. But if this value is a lot different, and and there is no local peak, then the full FEM side is probably the best option to go. Okay, the next questions are not related to my webinar, so I will reply to them just in the chat, and I will stop the broadcast here. And thank you all for your attention and for being here today, and I hope you find these new developments useful. Thank you all.